Welcome back, friends. In today's session we are going to continue with our topic of transportation, and as I said in the previous session that if anyone is in need of these notes, he or she can visit Kipaji app and then can buy the notes in a very low cost. And don't forget to subscribe to the channel, also to share the link of this video to your fellow students so that to easier the process of our study, especially in advanced biology, chemistry, physics, and mathematics subjects. Today we are going to continue with the factors affecting water potential. In the previous session, we discussed about the concept of water potential, and we said water potential is the measure of the tendency of movement of water from the one side to another. It's the measure of the tendency of movement of water, and if you remember, we said that the higher the water potential, the higher the tendency of water to move away from that side. So let's say if we have a solution having water potential which is -2, and another solution having water potential of -6, that means water will move from solution of water potential -2 to a solution with the water potential -6. So that means we are discussing about the movement of water. Tendency of movement of water is determined by water potential. Now, by knowing so, it is very important for us to know factors affecting the water potential and different calculations regarding water potential, which is our topic of focus in today's session. So we are saying that there are two factors affecting the water potential: solute potential and pressure potential. So we are writing a solute potential. We are writing solute potential as C. Then we are putting S below, and we are writing pressure potential as C. Then we are putting P below. So all of these, they will lead to something affecting it, which is water potential. So let's see how solute potential affect water potential and how pressure potential affect water potential. And then let's see the summation. How do we sum this one and this one to get to this one? What is the operation between them? So we are saying that solute potential, the effect of dissolving solute molecule in pure water is to reduce the concentration of water. But to increase the concentration of solute in the solution. Now, I know for some of you, you can be confusing yourself because of this statement. What we are saying here is that, let's say we have 1 liter of water. Assume we have 1 liter of water. And in this 1 liter of water, if this is pure water, that means we have, let's say, 1,000 grams of water. And remember, concentration we are calculating as mass divided by volume. Simply mass concentration. So concentration will be equal to 1,000 grams divided by volume, which is 1,000 cm cube. So you get concentration is equal to 1 gram per cm cube. That is concentration of a concentration for, or if you are putting the volume in dm cube, you can say concentration, because normally concentration is calculated in dm cube. Concentration is equal to 1,000 gram divided by dm cube will be equal to 1,000. Now, how addition of a solute tend to decrease this concentration? Remain with this answer in your head. We have got a gram per dm cube, 1,000 gram per dm cube. Now let's say in this 1 liter of water, we have added 100 grams of salt, 100 grams of sodium chloride. After adding 100 grams of sodium chloride, that means in order to maintain this volume of water, the volume of water now will not be 1 liter again, it will be increased. Depending on the density of sodium chloride, the volume of water will be decreased. Now let I know the density of sodium chloride is higher, is more than 1. But let sodium chloride have a density of 1. Have a density of 1. Having the density of 1, that means density is equal to mass divided by volume. The volume of sodium hydroxide will be is equal to density times mass. So it will be equal to 100 cm cube. Just letting, I know sodium chloride ina density kubwa ndio maana inazama kwenye maji. It sink in water. Now, assume kama tumeongeza 100 cm cube. I mean 100 cm cube. Ili tuweze kumaintain solution yetu ibaki kwenye 1 liter. That means 100 cm cube of water will be removed. So now, how many grams of pure water will remain? How many grams of pure water will remain? It will be the grams of pure water will be 900 grams. Why? It is because 100 grams they have been replaced by sodium chloride. So 900 grams, then calculating the concentration will be 900 gram per dm cube. And then concentration of salt, because a concentration is equal to mass divided by volume. Concentration of salt, which is sodium chloride in the solution, will be equal to 100 gram per dm cube. Now what I'm saying here is that adding salt to water will decrease concentration of water, but will increase concentration of solution. Or in other words, we are saying will increase the concentration of solute sodium chloride in the solution. So it will not be water, it will not be pure water again, but there will be increased concentration of solute in the solution. So that's what we are saying here, that reduce the concentration of water molecules and hence lower the water potential. So since water decrease, or the amount of water decrease when we are adding salt, the proportion or the fraction of water decrease. For example, if you have not understood this, just take again 1 liter of water, 1 liter, and then what is the proportion of water here in this solution? It is 1. Why it is 1? It is because there is no any other component. But let's add our add the 100 grams of sodium chloride. By adding 100 grams, then we have 1000 grams of water. Adding 100 grams, so we'll get the total grams 1100. So by taking this, now calculating the fraction of water will be equal to 1000 divided by 1100. If you calculate this, you will not get is equal to 1 because the proportion has decreased to almost, as you can see, to almost 10 over 11. 10 over 11, if we divide it by calculator, we'll get is equal to 0.9. So you see what happens. The proportion of water is decreased from 1 to 0.9 by adding 100 grams of sodium chloride. Hapo to involve calculation yote ya density. But the proportion of sodium chloride, kama ikiwa 100, let's say now we have 100 grams of sodium chloride. So the proportion of sodium chloride, let's say it is 0.101. Oh yeah, it is it is 1 minus, it is 0. This is 9.09, but this one is 0.090 or 0.91. So let's say this is the proportion of sodium chloride. Now adding 100 grams of sodium chloride again, we'll get 1200 grams of the solution as total mass. Now the proportion of water, calculating the proportion of water again, it will be 1000 divided by 1200. So you get 10 divided by 11. 10 divided by 11, which is 0.833. Now you see, but the proportion of sodium chloride has increased. Why? It is because taking 200 divided by 1200, 200 divided by 1200, you'll get 0.167. So you see, this is what happens. As you are increasing the solidity amount, you are decreasing the proportion of water, but you are increasing the proportion of salt. Thus, because you decrease the proportion of water, you are also decreasing the water potential, which is represented by the symbol C. So we are saying that all solutions, therefore, have lower water potential than pure water. The amount of this lowering is known as solute potential. Amount of lowering kutoka kwenye zero, we said that a pure water has the water potential which is zero, or which is assumed to be zero. So solute potential tend to decrease water potential from zero to a negative value. So solute potential is the measure of change in the water potential of the system. Measure of change in the water potential of a system due to the presence of solute molecules. So presence of solute molecules or introduction of solute molecules in the solution tend to decrease the water potential, and that the extent or the degree or the measure of decrease of the water potential is what you call solute potential. So solute potential is always negative. The more solute molecule present, the lower, more negative is solute potential. More negative is solute potential. Now from there, we have our pressure potential. We have pressure potential. If pressure is applied to pure water, or solution, it is water potential increases. So that means pressure potential tend to increase water potential. This is because the pressure is tending to force the water from one place to another. Such a situation may occur in living cells. So pressure potential, as I said that in osmosis, the water molecule, they are moving themselves because of the presence of kinetic energy, which tend to cause the random movement of particles. But if you apply pressure on the less concentrated solution, then water molecule, they can move fast as compared with the previous time. Kwa hiyo sasa, let's say here we have a container having two solutions, or having one solution divided in two sides with a different concentration of salt. So let's say this is side A, and let's say this is side B. So let's say side A is the concentrated or is the less concentrated solution, and this is the more concentrated solution. By the concept of osmosis, water will move from A to B by osmosis. And as I explained earlier, that if we apply pressure on this side, this pressure can stop the movement of water molecules from this side to this side. This pressure is called osmotic pressure. But my focus in this explanation is not focusing about the osmotic pressure, but it is focusing by discussing about the pressure potential. Now, pressure potential is that if we apply pressure on this side, let's call this pressure maybe P. If we apply this pressure P can increase the tendency of water molecule to move from A to B, or can increase the rate of osmosis. Remember, osmosis depends on the water potential. As we said that osmosis is the movement of water from the side of higher water potential to the side of lower water potential. Applying pressure will increase the water potential, and hence will increase the process of osmosis from solution A to B. Now, this pressure, or the extent or the measure of this pressure to affect water potential, is what we call the pressure potential. So we are saying that this is because the pressure is tending to force the water from one place to another, and this situation they occur even in the living cells. So example, when water enters plant cell by osmosis, pressure may build up inside the cell, making the cell target. That means inakuwa cell kama imetanuka. So cell inakuwa imetanuka na inafit kwenye cell wall. Kwa sababu gani? Plant they possess cell wall. So hata kama cell ikijaa maji haiwezi kabust. Kwa sababu gani? Kuna cell wall inayo prevent the excessive filling of water, and increases the pressure potential. So the pressure potential in a plant cell tend to increase when there is movement of water into the plant cell, and thus making the cell target. From there, Now we are saying that also water potential of blood plasma is raised to a positive value by high blood pressure in the glomerulus of the kidney. Water potential of blood plasma is raised to a positive value by high blood pressure in the glomerulus of the kidney. So hiyo ni example kwenye animal jinsi ambavyo pressure potential na water potential huwa inakuwa. Tunavyokuwa tuna high blood pressure kwenye glomerulus of the kidney, then water potential of blood inakuwa kubwa. Water potential of blood inakuwa kubwa. Now we are saying that pressure potential is usually positive, but in certain circumstances, as in xylem, when water is under tension or negative pressure, it may be negative. So it is always positive value, but sometimes in some of the circumstances it can be a negative value. So by definition, pressure potential, which is CP, is a little turbo pressure which can only develop to any extent of the cell wall is present, if the cell wall is present. So this is the turbo pressure ambayo inakuwa developed in the cell, na inaweza kuwa developed to different extents. Lakini if the cell wall is present, pressure potential, even increase in the pressure potential, cannot cause bursting of the cell. So we are saying that since water potential is affected by both solute potential and pressure potential, the following equation summarizes the relationship between the two terms. Water potential is equal to solute potential plus pressure potential. Water potential, which is represented as C, is equal to solute potential plus pressure potential. Note, solute potential is always negative and the pressure potential is always positive. So that means this one will tend to decrease the summation, but this one will tend to increase the summation. And the second thing to note is that in some books, gravity affects water potential. Gravity affects water potential. The vertical height of more than 5 meters tend to increase the effect on the water potential. So that's all we can say about the water potential. In some of the documents or in some of the books, of the reference books, you can read and then you can be told that gravity tend to affect water potential. Now let's move to another part in which we discuss about osmosis and the plant cell. Or we are saying the effect of solute concentration on plant cell. The effect of a solute concentration in plant cell, or osmosis in the plant cell. Now, what we are discussing in this part is about what will happen if water is moving either outside of the plant cell or into the plant cell. We are saying that the partially permeable membrane are of importance in water relations of plant cell, as shown in the figure below. You can get this figure from different resources such as a BS book or even from Google or anywhere. But if you can light the effect of solute concentration on a plant cell, then if you research, you will get these diagrams. Here we have 3 different conditions of the cell. We have the plasmolysed cell, that means it has undergone plasmolysis. Then you have a flaccid cell, which we will discuss the concept of flaccidity. And then we have the target cell, which we discuss the concept of turgidity. Now let's start discussing one concept after another. What is plasmolysis, or what does it mean when we are saying the cell is plasmolysed? If you dip a plant cell in hypertonic solution is the solution containing higher amount of solute relative to another solution. So in hypertonic solution here, this solution will contain higher amount of solute as compared with the fluid inside the plant cell. Now what will happen? Water will move from the plant cell to the solution, and this we are indicating it in arrows like this one, that there is the movement, outward movement of water from the plant cell to outside. Now what will happen? This is the cell membrane and this is the cell wall. So the cell membrane will tend to detach itself from the cell wall. Why? It is because of the plasmolysis, that there is the removal of water. The vacuole size tend to decrease and the cell membrane tend to detach itself from the cell wall. So you can see how the cell membrane tend to appear. Now it doesn't attach to the cell wall completely, but there are gaps which are here. These gaps, they don't have anything because water is removed. Now in those conditions in which the cell membrane has been detached from the cell wall, we are saying that the cell or the plant cell is plasmolized. Now from there we have the second phenomena in which we have the inward movement of water. Also we have the outward movement of water. That means in this condition, water is moved in, also water is moved out. So water tend to balance in the cell, and because it balances in the cell, then in some parts the cell membrane can detach from the cell wall, but it is only in a small extent. But in the great extent, the cell membrane has attached to the cell wall as usual. This is the normal condition of the plant cell in the isotonic solution. If you dip a plant cell in isotonic solution, that means the solution which is have the same concentration as the fluid surrounding the plant cell. In isotonic solution, the cell will appear like this way because there will be movement of water in, also outside of the cell. Now in this condition, we are saying that the cell, it is flaccid. From there, if you dip a plant cell in hypotonic solution, that means this solution is less concentrated, containing high amount of water as compared with the normal solution surrounding the plant cell. Now because this solution is less concentrated, that means movement of water by osmosis will be from outside of the cell into the cell. The cell will be filled with a lot of water, and by that filling with a lot of water will develop what we call the turgor pressure. So that turgor pressure will push the cell membrane, and the cell membrane will touch the cell wall like this way. You don't observe a space like this one or this one. Here it is because the cell membrane has been pushed by turgor pressure towards the cell wall. So there is a contact between the cell membrane and the cell wall because of the presence of turgor pressure caused by the accumulation of water in the plant cell. So by that way, we are saying that the cell here is turgid. And we shall see the importance of all of these aspects in the different parts of a plant. Now let's go to discuss in the notes and let's see the explanation of these things that we have discussed here. We are saying that the cell wall is usually freely permeable to substances in a solution. Freely permeable to substances in a solution. So it is not important in osmosis. Cell wall yenyewe inaruhusu solute, solvent. Cell wall haina shida yote, is always studied in cytology. The cell contains a large central vacuole whose contents, which is the cell sap, contributes to the solute potential of the cell. So the cell sap, which is the content of the vacuole, which is this one, the central vacuole, it contains cell sap and it contributes to the solute potential of the cell. The important membranes are the cell surface membrane and the tonoplast. Tonoplast is the membrane surrounding the vacuole, and the cell surface membrane is this one or this one, ambayo imeshrink hapo. Now let's see these phenomena of plasmolysis, flaccidity and turgidity. How are they taking place in the plant cell? So we are saying that if a plant cell is in contact with a solution of lower water potential than its own content, that means the solution will be more concentrated, or sometimes you call this as hypertonic. Hyper, that means higher. Tonic, hypertonic, higher concentration. Then water leaves the cell by osmosis through the cell surface membrane if the plant cell is in contact with the hypertonic solution. Now we are saying that water is lost first from the cytoplasm and then from the vacuole through the tonoplast. So water is lost from cytoplasm and then it will be lost from the vacuole by passing through the tonoplast membrane. So we are saying that the protoplast, that is the cytoplasm, that the living content of the cell, surrounded by cell wall. The protoplast, that is the living content of the cell, surrounded by the cell wall, shrinks and eventually pulls away from the cell wall. You see, the protoplast, all of the living content of the cell tend to shrink and then it pulls away from the cell wall. This process is called the plasmolysis, and the cell is said to be plasmolysed. That's why in the previous diagram I showed you the plasmolysed cell, that in the plasmolysed cell, if we are trying to draw the diagram again, in the plasmolysed cell we will have a cell like this way. Let's say is a plant cell like this way, and after having the plant cell like this way, this is the cell wall. So in the plasmolysed cell we will have the protoplast has been detached from this plant cell wall. So this is how the plasmolysed cell will tend to appear. So that means this is what we can call the protoplast has been detached from the cell wall. Now there are empty spaces here because of the loss of water from the cell, and the cell becomes plasmolysed. So by definition, the process of plasmolysis is the shrinking and pulling away from the cell wall of the protoplasm or the protoplast of plant cell when it is placed in contact with a solution of lower water potential than its own contents. So plasmolysis is very easy. Simply the shrinking or pulling away from the cell wall of the protoplast of the plant cell when it is placed in contact with a solution of lower water potential than its own content. Now, from there, also we have the terminology insufficient plasmolysis. Now, insufficient plasmolysis is simply a point. This is not the process in such as how we are discussing about the plasmolysis itself, but it is just the point at which plasmolysis tend to start. So the point at which plasmolysis is about to occur, or the point at which the detachment of the cell membrane or the detachment of the protoplast from the cell wall is about to occur, is what we are defining as the insufficient plasmolysis. At insufficient plasmolysis, the protoplast has just caused to exert any pressure against the wall, so the cell is flaccid. Now, in normal condition, if cell is filled with water, it will exert the pressure against the cell wall, and this pressure is what we call the turbo pressure. But in condition when water is removed from the cell, and if the cell has no enough water in order to produce or to create the turbo pressure, that means what will happen is that the cell will become flaccid. In a flaccid cell, there is no pressure in the protoplast which exert on the cell wall. So flaccidity is the condition at insufficient plasmolysis in which the protoplast has caused to exert any pressure against the wall. Or in other words, we can define that flaccidity is the phenomena which occur when the cell is placed in hypertonic solution, at which water potential of external solution is equal to water potential of contents. Actually, this is not the hypertonic, but it is the isotonic solution. If the water potential of the solution surrounding the cell is the same as the water potential of solution which is inside the cell, that is isotonic condition. But flaccidity, actually the phenomena. It is the phenomena. Even plasmolysis is just plasmolysis is the process, but flaccidity is the phenomena. So if we are moving from the normal cell with the turbo pressure to plasmolysis, before reaching plasmolysis, we are passing through insufficient plasmolysis. At insufficient plasmolysis, the condition of the cell is that the cell it is flaccid. So insufficient plasmolysis is like a point in the process of moving from a target cell to a plasmolysed cell. And at that point, the cell is said to be flaccidity, or is said to be flaccid. So we are saying that water will continue to leave the protoplast until its contents have the same water potential as the external solution. That's why, hapa ni hypertonic vile vile. Kwa sababu gani? Water inakuwa na leave, lakini inavyo leave mle ndani manake kabla haijafika kwenye plasmolysis inapita kwanza kwenye nini? Kwenye flaccidity au kwenye insufficient plasmolysis. So no further shrinkage then occur if solution of the outside now imekuwa ina water potential sawa na ile ya ndani, maana yake hakuna shrinkage itakayotokea zaidi hapo. Sasa unaweza kuuliza kwamba how comes solution ikuwa more concentrated then ina become isotonic? It is because unavoweka kwenye hypertonic solution, then after a certain time, yani ukiweka kwenye hypertonic solution, that means at first the solution is more concentrated, but as water moves from inside of the plant cell to outside, that means as the water moves, that means the concentration of that solution tends to decrease, and thus it becomes isotonic. Now the process of plasmolysis is usually reversible without permanent damage to the cell. Now we are saying that if a plasmolysed cell is placed in pure water or a solution of higher water potential than the contents of the cell, then water will enter the cell, and by entering the cell by osmosis, that means the cell will be returned to normal. That's why we are saying that it is a reversible process. As the volume of protoplast increases, it begins to exert pressure against the cell wall and stretches it. As the volume of water increases, it begins to exert pressure, which is pressure potential, against the wall and stretches it. The wall is strong and relatively rigid, as we know the nature of the plant cell wall. So the pressure inside the cell rises rapidly. The pressure is called the pressure potential and rises rapidly. As the pressure potential of the cell increases due to water entering by osmosis, the cell becomes target. Target, that means the cell or the protoplast start to exert a turbo pressure on the cell wall. So we are saying that fully turgidity, that is maximum pressure potential, is achieved when a cell is placed in pure water. When a cell is placed in pure water, then we are getting fully turgidity. But in other conditions, that means we are getting partial turgidity. So we are saying that turgidity, by definition, this occurs when a cell is in contact with a higher water potential solution, resulting into movement of water into the cell from the surrounding environment. So this tendency, the tendency of water to move from outside of the cell into the cell when the plant cell is placed in the solution with a higher water potential, this tendency or this phenomena is what we are calling as turgidity. So when the tendency of water to enter the cell is exactly balances by pressure potential, the amount of water leaving the cell is equal to that entering the cell. There is no further net uptake of water, and the cell now is in equilibrium with the surrounding solution. All of these processes, they tend to take place in the plant cell and they tend to be involved in different kinds of processes in the plants. Now the contents of the cell are still linked to be of lower solute potential than external solution, because only a small amount of water is needed to raise. Contents of the cell are still likely to be at lower solute potential than external solution, because only a small amount of water is needed to raise. So the pressure potential to the equilibrium point, and this is not sufficiently to dilute the cell contents significantly. The cell contents significantly. Kwa hiyo vitu ambavyo viko ndani ya cell huwa vinabakia kwenye higher solute potential. Kwa nini? Kwa sababu tunahitaji kiasi kidogo tu cha water ili kiweze kuongeza pressure potential. Hasa kishaongeza pressure potential to equilibrium, mle ndani mnakuwa bado mna solute nyingi. But because potential imeshafika equilibrium, tukishafika equilibrium, there is no need for us to change again anything. So we left things at the are. Pressure potential, therefore, accounts for the fact that at equilibrium the solute potential of the plant cell can still be lower, yani inabakia kuwa negative, can still be lower. Its content is more concentrated than that of the external solution. So this is the normal phenomena, kwamba the solute potential in the cell is always lower as compared with the external solution, because of addition of small amount of water which can raise the pressure potential of water and hence the water potential. So we are saying that pressure potential is a real pressure rather than a potential one. Pressure potential is a real pressure rather than a potential one, and can only develop to any extent if the cell wall is present. So the presence of cell wall in plants allows the plant cell to develop pressure potential to any extent, because it prevents the bursting of the cell wall. Now animal cells have no cell wall, and the cell surface membrane is too delicate to prevent the cell expanding and bursting in a solution of higher water potential. So animal cell must therefore be protected by osmoregulation. In plants there is no need of osmoregulation, because even a higher concentration of water in the cell cannot cause the bursting of the cell. But in animals we must protect the cells with osmoregulation mechanisms, as how we have studied in the Form 5 exclusion topic. From there we are saying that categories of solution based on the relative concentration. So if you remember, we said about the hypotonic, hyper and isotonic. These are the three basic categories of solution based on the concentration of a solute present in the solutions. In a hypertonic solution is the solution with a relatively higher solute potential than another solution, or than the inside of the cell placed into it. So if you put a solution, maybe a red blood cell, if you put a cell, maybe a red blood cell into a solution, and if that solution is hypertonic, that means it has a higher solute potential. As a result, water will move from inside to outside of the cell. If it is in plant cell, will lead to plasmolysis. So a cell under this condition will tend to shrink because of exosmosis. That means eggs moving water out, exosmosis of water from the cell to a hypertonic solution in which the cell is placed in. But a hypotonic solution is a solution with relatively lower solute potential than another solution, or than it is inside the cell placed in it. Under these conditions, a cell is at risk of bursting unless it has a cell wall because of endosmosis of water. So in a hypotonic solution, there will be endosmosis of water, that is the movement of water into the cell, and by moving water into the cell, that means you will increase the pressure potential, or you will increase the turbo pressure in the in the cell, and then the cell can burst if it doesn't have the cell wall. That's why in plant cell we have cell wall, in animal cell we have osmoregulation. Isotonic solution is the solution whose solute potential is the same as the solute potential of another solution or any cell placed in it. Water enters and leaves the cell at equal rate. So we have this diagram. This is a hypertonic solution. Water tends to move outside of the cell. This is our cell. Water tends to move outside of the cell. And in a hypotonic solution, water tends to enter into the cell. And in the isotonic, some water tend to enter and some tend to leave. And the rate of entry and the rate of leaving of water, it is the same. So if you are drawing maybe 4 arrows showing the movement of water into the cell, if you are drawing 4 arrows showing the movement of water into the cell, also you may draw 4 arrows showing the movement of water outside of the cell. So this is isotonic solution. This marks the end of our discussion regarding the factors affecting water potential and regarding the water and solute potential. Don't miss the next session. We'll be discussing about the solved examples. There are some calculation in this part, and in the next session we'll be discussing about those solved examples. We shall see how to calculate them and how to comment on them regarding the movement of water from one side of the plant cell to another side. If you need these notes, visit the Kipaj app. And if you don't understand anything in this session, look at my contact in the description below, and you may call me by the need or for the need of discussion, past papers, and any updates about my sessions. You may join my Telegram group using the link below in the advanced group, Dr. Mlelwa A-level students. Thank you, everybody, and later wish you nice studies.